we are going to be starting to do more kind of polynomial analysis that you were used to from past years. So this is where all of your questions last class, could we just do this? Now we're about to just say yes, okay? To make sure you are comfortable with all those things, we're going to make sure we understand the graphs of some simple parent equations like x, negative x, x squared, negative x squared, et cetera, et cetera. If you guys know what the sketches are, please sketch them. Sketch all 6 of them. If you're wrong, who cares? Just check with your neighbors. Let's see if you remember. Because if you know the graphs of x, negative x, x squared, negative x squared, x cubed. I saw that once. I love it. Negative x cubed. X to the fourth, negative x to the fourth. You're actually good for like most of this lesson, like 2/3 of this lesson. Okay? Good. Love the idea, not the perfect y equals x to the fourth equation. But that's what an x to the fourth is. Okay? Yep, nailed it. Okay. So this is y equals x, y equals negative x. This is x squared, negative x squared. X cubed, negative x cubed, x to the fourth. A little bit steeper, but slows down longer than x squared. A little bit steeper, slows down a little bit more. Second. Okay, and if you got wrong, don't worry about it. You're thinking 1 over x. Okay, now stay here, stay here, stay here. Because understanding just these graphs help you understand polynomial graphs tremendously. Lots of information about these graphs. For example, let's look at our odd degree, y equals x and y equals x cubed. What did we know about odd multiplicities? We changed signs. Boom, boom, we notice sign changes. Boom, boom, we notice sign changes. So if we're looking at the zeros, we can see sign changes. We go from negatives to positives, or positives to negatives, both with y equals x or y equals x cubed. So sign changes occur for odd multiplicities. But we can see we kind of just pass straight through. Here, x equals 0 is our 0, but its multiplicity is 1 because we just have x to the first. We can see, if you understand y equals x, it makes sense that y equals, or having a 0 with a multiplicity of 1 would go right through the x-axis just like y equals x does. Multiplicities of 1 will pass through the x-axis while they change sign. Odd multiplicities bigger than that will kind of bend on their way through. We can see an odd multiplicity. We see x equals 0 has a multiplicity of 3. We're going to bend on the way through. Kind of slows down as we change signs. Cool? So we know odd multiplicities from last class change signs. So now we're going to be a little bit more specific about that. Keep here, stay here, stay here, stay here. Now let's look at even. X squared and x to the fourth. We remember from last class that even multiplicities don't change signs. Okay. So here we have x equals 0 would be a 0 of y equals x squared, and we can see the multiplicity is 2. We don't have a sign change, no sign change here. We could see we go from positives and then to positives, or we go from negatives to negatives. Well, instead of saying no sign change, we could continue to say that. We're going to say we have a bounce. We bounce off the x-axis. Why? Because we're squaring things. Even powers retain signs. Either a negative even will stay negative after a 0, or positive even will stay positive. We see right here, same thing. Here, x equals 0, multiplicity is 4. We don't change signs, we bounce. Just by knowing these 4 graphs, we can also pay attention to the ends. Look at y equals x. It is an odd degree, an odd power. Boom, we end like that. Let's look at the ends of y equals x cubed. The ends of y equals x cubed are the same. Y equals x, y equals x cubed. Y equals negative x, y equals negative x cubed. Just by knowing the graph of these simple parent functions, you start to notice patterns that you'll be able to use when you analyze your polynomial. If you look at your evens, x squared, x to the 4th, your evens are ending up in the same direction, whether you have a positive x to the 4th or a negative x to the 4th. By understanding just these simple graphs of parents, you will be able to use this information to help you understand more complex polynomials. Okay? So, 2 things, multiplicities and now end behavior. Okay? Here we go. Multiplicity of 1. We said that there was a sign change. Great. But we're going to be more specific. We passed right through your 0 when you change your sign. It's just like y equals x, whose multiplicity is 1, passes straight through. More odd multiplicities also change signs, like a multiplicity of 3 will have a sign change, a multiplicity of 5 will have a sign change. We knew this from last class, but now, just like y equals x cubed, we understand that when we change signs, we kind of slow down. Why do we slow down? Why don't we speed up? Why doesn't it go through 0 faster? Tell your neighbors. Why don't we just like, whoa, go really fast through 0? Why do we slow down? Why do we bend? Because what? Bending is fun, yes. Why do we bend? What? Does it matter that we bend?
Like, does it matter we know why?
Well, it's good to think about things sometimes, I wonder. I could just tell you everything and you'd be like, okay, but maybe not like stretching your brain muscles out, really understanding. Maybe it won't stick with you. So what do you think? Why does it slow down? Why doesn't it speed up? Here's what I do. What I think about it is I use like the idea of 1. You know, y equals x 1, 1, a half, 0.1, 0.1. Okay? Yeah, that also has 1, 1, x cubed. But what happens if you take a fraction like a half and cube it? What's 1/2 cubed, Linder? That's a question for you. What's a half times a half times a half? Great, Linder. Way to answer with confidence. How about what is a 1/3 cubed? Good. We take a fraction and cube it, and it actually gets smaller. So instead of having this 0.5, we have this 0.5.125. Why do we bend? It's the fact that when you cube decimals, it actually gets smaller. So we get like closer to 0, slow down. That's why. Good to just stretch your brain muscles out sometimes. We thought that even multiplicities are no sign change. We are correct. We have seen what happens when you don't have a sign change. You hit your 0, you go back where you come from. We'll call that a bounce. All good. We already kind of knew this about multiplicities with this being something new. All that is different about today, I'm just going to do one, you're going to do the other one, skip the third one because it's asking you for an inequality. I don't really care. All that's different today is if you see a multiplicity of 3, make sure you bend. Oops, 3. Make sure you're going to bend when you sketch your graph. I believe on your homeworks as well as your quiz, you did not have any multiplicities of 3s that we asked you to sketch. We did ask you to do sign chart analysis, but we didn't ask you to sketch. Now we're going to ask you to sketch with multiplicities of 3. Just make sure you are like, oh, we're going to bend through. Make sure for the multiplicities of 1, you go right through, just like y equals x goes right through. I'm putting a PT next to it. That means like we pass through. What did your Algebra 2 teachers say? Just like pass through, goes through, nothing weird. All right, cool. All right, so -2, 0, 3. Now, we could incorporate what we're about to do on the next page into our graph, where we talk about end behavior. You could do that. I still like test points. I'm still comfortable with test points. I'm still comfortable filling out a sign chart and then doing my graph. So I'm still going to say I got positives here when I plug in 4. I'm going to change signs at 3. I'm going to change signs at 0. And I'm going to change signs at -2. Like, we can still do this. There's no even degree. There's no bounce. There's no sign change. I'm still going to do this. The only thing I'm going to just make sure I do is that 0 bend. You can go right to left. You can go left to right. Whatever you want to do, you'll start negatives. We'll talk about end behavior and another way to get that later. Positives. Slow down as you get through that 0, negatives, positives. Whoops. Stuff on this guy. On your quiz, just like make sure you write the word bend, okay? Just it'll help, okay? Because like some people think that drawing bend. All right, do the next one. You don't have to use the sign chart. You can use what we're going to call end behavior, which we kind of looked at with x squared, and x cubed, and x to the 4th. But go ahead and sketch the second one. Try to bend, though. Like, try. Try to bend. So, like, but it's not even attempting. Slow down, bend on the way through. Okay? Slow down. And no, bends are tough. Slow down, bend on the way through. Ready? Think like x cubed. X cubed, right? You sketched x cubed. I saw you. See? That's a bend. Try to recreate that right there. So let's be going like a negative x cubed. Yeah, there we go. Better. Okay, think x cubed. X cubed, multiplicity of 3. If you understand and you guys sketch what x cubed looks like, you understand what a bend looks like. Check with your neighbors. What are we getting? Stuff you've already done. Okay? So, nothing crazy. Nice. This will be like some multiple choice questions. Yeah, sure. It is part of Unit 1. You guys have 3 units that are on the AP exam. Yeah, but like each unit is a lot. All right. Again, I'm going to use sign charts. You don't have to use sign charts. I'm going to use sign charts. I plug in something like 5, negative, positive, positive. I know that's a negative. I know at 4, I'm going to bend. A bend is a sign change. I know at 2, since the multiplicity is 2, there is no sign change. I'm now going to refer that as to a bounce. If you just say no sign change, like that's great. You could keep doing that. That's fine. So no sign change. At 0, I still have a multiplicity of 1. I'm just going to pass straight through. I will change signs. And now you could sketch your graph from left to right to left, whatever you want. We got negatives through our 0 normally. We will bounce off of that 0. Okay, here we go. Let's see if we can do it. We will slow down and bend on the way down. Cool? Something like that. That's not bad, right? It's not bad. Yeah, all right, I'm getting better. All right, cool. What do we notice? Fact, between any 2 zeros, you're going to have a max or a min. This is something that you will see sometimes on the test where it's like, hey, how many maxes and mins does this have? Well, if you could sketch the graph, you can kind of see max, max, min. Now, what do we call this location of a bounce? This ends up tangent to the x-axis. This is new, but it like shows up. We saw one test question where it looked where that showed up, and I'm like, ooh, kids aren't going to know that. It's like, well, a bounce is a tangent to the x-axis. What does tangent mean to you?
Perpendicular.
You don't know that.
One is perpendicular to a person and subsequent to one point.
Love it. Who remembers geometry? Who remembers circles? Do you shake your head so adamantly? I'm going to tell you geometry teacher. I can look this up. Who's your geometry teacher?
She's not here anymore. One here.
Who?
Okay.
Oh, cool. I have her cell phone number. We're good.
Oh.
Circles. Lines that just touch circles in one location are called tangents. Okay? This just touching means this line ends up just touching that graph at that location. This is something that might be required for you guys to understand that a bounce creates this idea of a tangent. We'll talk a lot about tangent lines in calculus. Max, max, min, in between 2 zeros, max. Bounces are always maxes or mins. Whenever you have a bounce, you will definitely have a max or a min. Okay? And when you have a bounce, you'll be tangent to the x-axis. That's a max, that's a min. This is not tangent to the x-axis. Actually, it is, but like, whatever. Just, who cares? Just little things to think about for the future. Okay. Now, let's talk about the ends of our graph. What is going on all the way to the right and all the way to the left of our graph? Now, when we look all the way to the right, we're thinking about plugging in larger and larger and larger values for x. Okay? 10, 20, 30, 40, 50. Okay, let's keep it. 100, 2, no, it's 1,000, 5,000, no, like 1,000,000, 20 million, a Google, 20 Googles. We're thinking about what's going on all the way to the right of infinity. If we're talking about the other end, we're thinking what's going on all the way over here at negative infinity. And your math teachers told you, look at this last one here, that when you're talking about all the way to the right and all the way to the left, or something like this, that you only had to pay attention to one thing. What was that one thing? Tell your neighbors. Man's What was the one thing out of that equation, negative 2x to the fourth plus 300x cubed minus 4,000x squared? What was the one thing you had to pay attention to when we're talking about the end? Yeah. You were told from previous math classes that the behavior at the ends will be determined by the degree of the polynomial. Now, the degree of the polynomial is like the largest degreed term and the sign of its leading coefficient. You were told that if you have that big polynomial in that bottom right corner, that you only had to pay attention to negative 2x to the fourth. I'm going to challenge you guys to make sure you understand why. Because I did a little investigation myself. And I graphed negative 2x to the fourth, that first equation in the top left. And I'm like, okay, looks good. The ends of negative 2x to the fourth look like x to the fourth. They're down and down. Cool? But then I graphed negative 2x to the fourth plus 300x cubed. And all of a sudden, I'm like, oh, hold on a second. It looks like the ends look more like this cube. Pay attention to the lesson. So you guys are telling me that this is what I have to pay attention to, which means that my ends are going to look like this, but I just graphed that, and it looks like my ends are down and up. Tell me, who's right? Were your teachers last year right? Or is what I'm seeing right now right? Please discuss with your neighbors, and then I'll come back to you. Thanks. Go. Sure, there's zeros and zero. Whatever. Zoom out. Oh. Zoom out. All right, fine. Fang, you had your hand raised. You really want to talk about this. What were you going to say? Sure. Nailed it. What Fang was just saying was, yo, zoom out, Mr. Messner. Okay? So, let's zoom out. 100. Okay. Okay, negative 100. All right. 1,000. I don't know. Negative 1,000. Negative 10,000, 10,000. Okay, move the x's too. Negative 10, 10. I don't know, Fang. Maybe more? All right, let's see. Add a zero. Add a zero.
All right, that should make my head.
Move the x's. Negative 100. 100. I don't know. Let's go back. Let me get enough zeros here so I can see. Let's add another 0. Add another 0. Whoa! Hold on a second. What did you just see? What are you seeing? Let's go to 1,000. Oh, there it is. Yeah, so your teachers were right, but it's fun to see it, you know? If you guys, it did not take way too long. If you guys don't think big, and what's thinking big? Zooming out, like infinities, maybe you're going to miss the fact that, yes, when you plug in large numbers, this is important, and this is important in calculus. This infinity is going to be so much bigger than these infinities that this infinity will dominate things. Adding these smaller infinities are like adding small decimals to really large numbers. So, your math teachers who just told you were right. You just care about the biggest degree terms, okay? And y equals negative 2x to the fourth plus anything that's less than that will always have negative x to the even end behavior. Where was the end behavior? Well, going back to our first page, the arrows were the ends of our graph. If we paid attention, we saw the consistencies. X squared, x to the fourth, were up and up or down and down. X to the first, x cubed, will go in an opposite direction. So, what you will do is understand your end behavior, and then you will make sure you can tell me the end behavior using limit notation. Now, this is going to be new for all of you. You guys have all been using infinities before. We're just going to be putting infinities into a more mathematical statement versus using a lot of arrows. Okay? Let's talk about this one. To the left, I'm going down. We would say that the limit as x approaches, okay, we're talking about x's. So as our x's go to negative infinity, this is me saying I'm looking to the left. Cool? My graph, my function, my f of x, whatever we have, is going down. We would say that my y's are approaching negative infinity. This is our left end behavior. To the right, looking at this guy, I would say that the limit, this is an undercase LIM, as x approaches positive infinity, if I go to the right, my function, my graph, whatever equation I have, my f of x, would approach, and then we pick the correct infinity for my y. Since I'm going down, we would say I'm approaching negative infinity. Cool? This is the same as what you guys did last year, only last year you were like, x goes to negative infinity, y's go to negative infinity. It's the same thing. Got it? Only this goes underneath a limit, and this goes as your answer. Got it? Okay. So, if you encounter a positive x to an even, let's use our arms. What would a positive x to the even look like at the end? Go. Everybody does this in every math class. Go. Thomas, do it. Positive x to the even. What would it look like at the end? Cool. What does this look like? Touchdown. Touchdown. Like, or it looks like positive x squared. You can always remember for multiplicity and for end behavior, simple graphs. Y equals x squared, touchdown. What about negative x to the even? What does that look like? Use your arms. What does that look like? Negative x to the even. All right, what's it look like? What's this look like? Come on, give me some. Yo, it looks like negative x squared, sure, but like, what else? It's not a touchdown. Table, sure. It's an angry gorilla. That's what I said. It's an angry gorilla. Okay. Now, touchdown, angry gorilla. X squared, negative x squared. If you know x squared and negative x squared, you know any x to the even end behavior. Okay? Because you saw x to the fourth looks just like x squared. Cool. So, angry gorilla. Positive x to the odd. Arms, go. Positive x to the odd. You know what I do? Y equals x. I know what y equals x looks like. And then I just flex a little bit for the x cubed. Okay? That's all. That's all. Okay? Y equals x cubed. Y equals x cubed. That's all. You gotta flex sometimes, you know? Doesn't matter if you're weak, like I am. You gotta flex sometimes. Okay? Y equals x, flex, and you got y equals x cubed. I like to call it John Travolta. Don't think you're an Egyptian. Egyptians are the cubed root of x. No. We are strong x cubed individuals, okay? There you go. So don't be an Egyptian. Negative x to the odd. Negative x to the odd, just like flex the other way. Yo, do you guys see the weight room that way? Or is it that way? All right, I'll check it out. That's negative x for the one thing. I'll go check it out. All right, cool. So, all you care about, just like your Algebra 2 teachers said, and they were correct, is the highest degree term. Because if you zoom out enough, eventually the x cubed term is going to win. It was fun to see that, though. So I don't care about the other ones. And again, we're just talking about our end behavior. I have a negative x to the odd. We're flexing in the correct direction. Think about x cubed, flip it. Think about y equals x, flip it. You have a negative x to the odd. If you need to draw a y-axis and an x-axis, do it. Draw your line. Do it. I like to put negative infinity first. When you're going to the left versus when you're going to the right. These infinities in black. That's the left. This is the right. These infinities are ups and downs. This is, look at it. What's the limit as x approaches negative infinity? If my x's are going towards negative infinity, that's left. My x's are going to positive infinity, that's right. Negative infinity, x's. Positive infinity, x's. Cool? No, the arrow is pointing towards the x that you're plugging in. So I write down negative infinity, Woods. Okay? Okay. When I go to the left, my y's are going up towards positive infinity. This positive infinity is up. That positive infinity is right. That negative infinity is left. If I go to the right, my y's are going down. This negative infinity represents a down, it represents a y. Got it? All right, do the next one. Do the next one and the last one. The third one. Do the third one too. Do them all. Take with your neighbors. Go. Do them all and take with your neighbors. Go. Check with your neighbors. Go. 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 Check. Check. I didn't check. You didn't check. Google didn't finish. Check with Google. Nope. Check. Yo, don't get these wrong. None of you are actually drawing lines. You guys are all too cool. Not you, thank you.
I was drawing mine.
Yes, it helps.
I'm a big drawing mine.
I'm a big visual guy too. Visualizations help understand. Oh, positive x to the fourth. Positive even. Evens are easy. You're up and up or down and down. This one's up and up. So negative infinity, positive infinity are both going towards positive infinity because we're going up. The next one, also easy, but you have to identify that the negative 4x to the fourth wins. Negative, even. This is our down and our down. To the left and to the right, we are going down. That's easy. It's the odds that people make mistakes on, which is why we give you more odds than evens for your quizzes and your tests. 2x to the fifth, because that's what we do. Wins. Not the 50x cubed. 2x to the fifth. Positive, odd. I think of y equals x. I flex a little bit. So y equals x cubed. I know this is what the end behavior is going to look like. Either of those, I need to make sure in the right directions, I got the right sign. As I go to the left, that's a left. As I'm going to the left, my y's are going down. As I'm going to the right, this is a right. My y's are going up. Come on, guys. Don't be sloppy / think that it's easier. Draw a couple lines. Help yourself out. Understanding x infinities and y's infinities mean two different things. Negative left, positive right, or negative down, positive up. Angry gorillas, touchdown. That's a good angry gorilla. If I give you a graph, you can give me the limit statements. Do this one on the right. Go. Give me the limit statements about the end behavior. As we go to the left, my graph is going up. As we go to the right, my graph is going down. Got it? Like, which way is my arm pointing? Cool. All right, that's 2/3 of the lesson and the last third. Now that we know everything, Mr. Esser. Last name? Yeah. Sure.
No.
Okay. Here's what we can do. We can be given a graph and we can write the equation. Now, what are some of the information we have? We have that this is some sort of odd degree. Okay, we could use that to our advantage. This is some sort of negative x to the odd. We can use that to our advantage. What else do we know? We know we have a 0 at x equals -1. We know its multiplicity has to be 2 because you see a bounce. We know x equals 3. We're passing through. The multiplicity has to be 1. Now, actually, one of my statements that I just made could be false. Which one? Nailed it. Good. You don't know that this is 2. This could be 4. Could be 6. We are always going to give you the least one. So, like, just go ahead and assume it's 2. It'll make things easier on you. Cool? We're not gonna trick you and give you like, oh no, that was a 4th degree multiplicity. You know what I mean? So just assume it's a 2, a 1, or a 3. Cool. Great. Now, could you write out maybe a general form of your equation, but not being very specific, using these factors? Okay, what would be some of the factors if -1 is a 0 and 3 is a 0? Tell your neighbors. Good. A lot of students trip up on this, but hopefully your mistakes last year, you're not going to make this year. X plus 1 must be a factor because we saw like when we have x plus 1, -1, there is my 0. So x plus 1 is my factor, but it's going to be squared. And then x minus 3 has to be a factor so that 3 plugged in gives me a 0. Very good. You guys remember that from last year. I'll tell you Algebra 2 teachers. Now, possibly we have a negative leading coefficient. Now, this could be the equation. You'll have some questions on your homework says, what could be the equation? Now, you could see that we have negative x to an odd. You could just say, okay, negative, this will be an x to the odd. We're good. But sometimes we will ask you, what must be the equation? What is this exact value of this leading coefficient? So, a negative is a good understanding, but sometimes I want the value. So, we will be giving you extra information sometimes, like a point. That's a point on the graph. That means when you plug in 0 for x, your y better be 6. How can we do that? When you plug in 0 for x, your y better be 6. You can set up an equation to solve and find this exact leading coefficient. We get 6 equals a times 1 times -3. A's got to be -2. Oh yeah, that makes sense. A negative value, because we have a negative x to the odd, is good. Leave it in factored form. But boy. Okay. That wasn't for you, Thomas. That was for me, okay? Okay, all right. That was for us, then. Respect. Respect. We're just getting some depth, and that's okay. All right. Go. What must be this equation?
They're my homework. My helmet.
What is the information we have? Well, it's got to be a negative x to the 4th. Okay, that could be an equation, sure. X equals 0 has to have a multiplicity of 2. X equals -2 has a multiplicity of 2. Cool. This could be an equation, negative x squared times x plus 2 squared. But let's try to be a little bit more exact. must be the equation. Well, what is the extra piece of information I have? When x is -1, y is -3. Cool? Use that to your advantage. When x is -1, y is -3. Go. A is -3. So your equation is -3x squared, x plus 2 squared. All right, guys, don't flex too much while you're doing your homework. I don't want you to hurt yourselves, all right?
Here, forward.